So our next speaker is Amelie Saintonge from University College London, who will talk to us on probing galaxy evolution with dust and gas. Amelie.
Right, good afternoon. I'm very pleased to be here to deliver this talk following the award of the Fowler Award last year, already a year ago. So as the previous speaker mentioned, these prizes are quite rare. There's very few such prizes for people, especially at the early stages of their career. So they are quite an honor and can make a difference on one's career. So thank you very much for making this possible. My research is in the general field of galaxy evolution. So since we have a very broad audience today, I wanted to set the stage by giving sort of 100 years of galaxy evolution history in about 3 slides. So I've had to make some quite significant editorial choices here, so please forgive me for what's missing. But the things I want to point out is just to highlight how simple yet complex a problem this is. So I've put some pictures here that are from the seminal paper by Edwin Hubble in 1926, where he, for the first time, presented a classification scheme for galaxies. And just to put things in context, right, 1926, this is 6 years after the great debate where the very existence of external galaxies was being debated, right? So we go from not even knowing that galaxies exist to 6 years later having images like this and be able to put together a classification scheme where galaxies fall into 2 broad categories. Either they are spiral and star-forming, or they are more elliptical looking and quiescent. And to this day, this is still the classification scheme we use for galaxies. So this is a very, very striking feature of the galaxy population, but that we still struggle to completely explain this. We do not have a complete ab initio model for galaxy formation and evolution. It is still a topic of intense study. The first sort of theories for convincingly explaining how a galaxy form didn't emerge until sort of the 60s. And then we had another burst in discovery in the last couple of decades, really due to the increase in the sizes of samples that we have access to all across the electromagnetic spectrum. So I'm just pointing out a few here to illustrate my point, but I think it's fair to say that the Sloan Digital Sky Survey has been revolutionary in several areas of astrophysics, and galaxy evolution being one of them, because it's allowed us to not only image, but to take spectra of millions of galaxies. So we can not only look at shapes and colors like Hubble did back in the day, but we can measure countless properties about their chemical properties, the way they rotate, whether or not they have supermassive black holes, et cetera, et cetera. So the name of the game in the galaxy evolution business is really to establish a vast network of scaling relations between all these properties of galaxies, and then use these relations to connect to the physics that might explain why galaxies form and evolve to what we see in the universe today. Thankfully, we have observations, as I said, all across the electromagnetic spectrum. So thanks to space telescopes like the Herschel Space Observatory that observed in the infrared, we can measure fundamental quantities of galaxies, such as the rate at which they form new stars. And because of telescopes like Hubble, we can not only do these studies in the universe around us, but push all the way back to the very first galaxies in the universe. I told you this was going to be a quick introduction. So we're at the stage where I'm just going to introduce what is sort of our current consensus view of galaxy evolution. So as Hubble pointed out to us nearly 100 years ago, galaxies mostly fall into categories, right? So I'm representing the entire galaxy population on this diagram. So on the x-axis we have the mass of the galaxy, and the y-axis is the rate at which stars are formed in these galaxies. So we have a sequence of what the star-forming galaxies. So these are the spiral galaxies like the Milky Way or Andromeda. And then there's a separate distinct population here of red elliptical galaxies. And it's very two clear population with a small transition zone between the two. Because we can do these observations, up to a few billion years after the Big Bang, we can track this sequence of star-forming galaxies, not only in the local universe, but to higher and higher redshift. So that gives us a relatively simple and, I have to say, satisfying picture for galaxy evolution because of the tightness of this relation and its observed evolution with time. If I'm presented with a galaxy, I can relatively accurately predict the rate at which it forms stars, simply based on its mass and the epoch at which I'm observing it, which tells us something quite fundamental about the process of galaxy evolution. The main mechanism have to be things that operate on long time scale, right? It has to be something that is steady and that operates on these long time scales. So, as I said, we have these exquisite observations, yet we are still lacking a clear explanation for why all of this happens. And so I'm going to pick one of the open questions in galaxy evolution studies, and I'm going to illustrate how we can make progress on such a question. So one of the big questions is, how do galaxies evolve from the star-forming sequence here down to this part of the diagram? How do we turn star-forming spiral galaxies into these passive elliptical galaxies? So it's a very, very long-standing question, and it's difficult because there are very many mechanisms that one can think of that could explain this transformation. So, as an example, so I've picked here a given mass in this diagram and picked two galaxies as examples. These galaxies have exactly the same mass. One of them is forming stars at a healthy rate, and this galaxy, same mass, but for some reason it's not forming stars nearly as much. We need to understand why, right? That's a very basic question. So I'm going to replace the actual pictures with these cartoons. So our normal star-forming galaxies, so the gray represents the mass, the stars in the galaxy, and the purple are the newly formed stars, right? So these two galaxies have the same mass. This one forms a lot of stars, this one very little. Now, if that's all the information I have, it's actually very difficult to explain why that might be the case, right? So my whole angle on this question of galaxy evolution is to introduce the study of the gas in the galaxies as part of our big toolbox to understand galaxy evolution. And it becomes something like this. So now the blue here represents how much gas there is in the galaxies. So that leads to, so if we compare our normal star-forming galaxy to our poorly star-forming galaxy, we come up with two possible different explanations, right? It could be that this galaxy is forming little amount of star because, at fixed amount of gas, it is inefficient at producing new stars. Or, alternatively, it could just be that it is very poor in gas, but forms stars out of this gas at a normal rate. Right? So these are two fundamentally different explanations for why this galaxy does not produce a lot of stars. And knowing which one it is will make it much, much, much easier for us to explain why this galaxy is not forming star, right? To link it to the actual physics. So that's the idea. So we really want to have a look at the gas in these galaxies, right? Because it is such a critical part of the growth of galaxies. The problem is that these observations are quite challenging. So to put things in context, I'm showing you the mass budget of a galaxy a bit like the Milky Way. So the vast majority of the mass of a galaxy is in its dark matter, which for observers like myself is a complication. It's very difficult to probe that directly. The remaining, so what we see of galaxies, the stars, right? It's only about 5% of the total mass of the galaxy. And what I'm talking about, all the cold gas in the disk of the galaxy, it's barely 1% here. So we're going to zoom out of that. So now if I look at 1% and I break it down, right, about a third of that is the molecular gas, and only about 1% is the dust. Now, I'll leave the dust aside, but this dust, this 1% of 1%, this tiny, tiny thing, turns out to be a vital tool in order to understand the growth of galaxies. And I'll come back to that in a minute. But for now, I'll focus on the gas component. So I've been very lucky to have had the chance to be involved with some of the very best and very largest surveys for cold gas in large sample of galaxies. So we've done these surveys with these telescopes, which are run by the IRAM Observatory. And they've allowed us to get a complete view of gas across the local galaxy population. Now, to put things in context, so if this is all the galaxies for which we have a spectrum of the optical light, so spectrum of the light coming from the stars and the gas, from the Sloan Digital Sky Survey. This is how many galaxies we have with a spectrum that tells us something about the cold neutral gas in the galaxies. Alfalfa is the survey I worked on incidentally for my PhD. So this is about 30,000 galaxies compared to 1 million galaxies. And now if you put X cold gas, so this molecular gas survey I'm going to talk to you about later. Now I'm just going to zoom in on this. So this is the last 10 years of my career, so just so it doesn't look too insignificant, we'll make sure it actually appears on this. So this is 500 galaxies. This is state of the art. This is the largest comprehensive sample we have for molecular gas in nearby galaxies. The reason it's extremely time consuming. And so these 500 galaxies, it's about 1,000 hours of telescope time. So 100 nights at the telescope getting these data. So rate about 5 galaxies per night, as opposed to something like SDSS, where you can get 5,000 spectra per night. But, it's worth the effort. So I'll go back to my example earlier and show you an example of what we can do once we have these measurements. So now I'm back to showing you this star formation rate mass diagram. And now all the blue dots are all these galaxies for which we've painstakingly acquired these measurements of their molecular gas. So the basic question I'm going to try to pose is to see whether we can use the gas content to explain why the galaxies populate this plane like this. Why do we have star-forming galaxies and why do we have these passive galaxies? So as an illustration, so I've put down these boxes, right? So in each of these boxes, I'm going to calculate what's the mean gas content of these galaxies. And I'm going to compare that to their star formation ability, and we'll see if it all adds up. So to do this exercise, we need a benchmark. So this is what we have on the right here. So it's the same boxes, and I've color-coded them by what's the mean sort of star formation activity in each of these boxes. Now this star formation, this is this specific star formation rate, so star formation rate over mass, and then I've done a bit of a thing like you do in the Drake equation, so you trivially expand an equation to make other terms appear in there. So when I do that, I get access to some of these quantities, right? So the first term here tells me about just the size of the gas reservoir of those galaxies. The second one tells me about how much of the gas is actually dense enough to form molecules and to actually form stars. And the last term here tells me how efficiently the galaxy converts the gas into stars. So let's look at these terms one by one and see how well we do. So on the left here, so same boxes, now I'm showing you this mean gas fraction. So this is the total cold gas reservoir of the galaxies. And I've normalized things such that you can compare the two things equally. So if gas, cold gas, the extended reservoir was enough to explain everything, these two things would match perfectly. Now you can see it's not bad, right? There's definitely a lot of similarities. But there's a few problems, right? We are lacking a bit of dynamic range. We can't quite explain the very high star formation rates over here. So what I'm going to do is add the second term here. So now what we're looking at when we combine these two things is the amount of molecular gas. How much gas is sort of in dense molecular clouds in these galaxies. And now we have this. So it's looking better, right? We have lost some of the trend with mass we had in the previous plot, but we're still lacking in dynamic range, right? This is not blue enough, and, well, you'll have to take my word, but this is not quite the same red as that red over there. So we have a bit of a problem down there as well. So what's the last? I mean, if you're following, you might suspect that the this term will be important now, right? So this is what we're looking at here. So this is, the gray line here is our same benchmark. So we have sort of normal galaxies in this gray band. We have highly star-forming galaxies on the right, and these passive ellipticals on the left here. The black line shows the mean gas content, and the magenta line here is this star formation efficiency. So what we see is that these galaxies that are very actively star-forming, they are more gas-rich than normal galaxy. But in addition, they are more efficient at converting their gas into stars, right? And it's roughly an equal contribution of the two effects. And as you go the other way, you found the opposite. Our passive, not star-forming elliptical galaxies, they're very gas-poor, so that's part of the problem. But on top of it, the poor things, they're less efficient at converting that gas into stars. So now we have the tools to actually answer this question we posed earlier, right? If we're comparing this star-forming galaxy with a galaxy of the same mass, but that doesn't form more stars, and we were wondering, what's the explanation here? So we can actually, by looking at the gas, we can disentangle, the star formation efficiency and how much gas there is. And what you find is that as galaxies go from being on the main sequence here, so we're looking at the gas content here, right? And you see how the gas content lowers as we go down here, and at the same time, the star formation efficiency. So the explanation why these galaxies are not forming stars, it's actually, a contribution of these two phenomena I was explaining earlier. So this is just one example, right? One type of observation, one question. We've been doing this, observing all the different phases of the interstellar medium, looking at gas well outside the star-forming disks of galaxies as well. And with all of that, this is the modern view of galaxies, right? What we think of the galaxy when we think, if you close your eyes and you picture a galaxy, right? What you see, a spiral galaxy, it's only this very central part here, right? We have to think of galaxies as these very large ecosystems, these galaxies that are fed by filaments bringing in fresh gas into these galaxies. Now that new gas triggers the formation of new stars, and the energy released by the star formation process then pushes gas back out of the galaxy, some of which will then fall back. And so we have this constant dynamic cycling of material in and out of galaxies. So this, it's quite a sort of a change in our perception of galaxies from being, things that formed all at once early on in the history of the universe to these things that are constantly evolving through these gas cycles. Now, if I go back to this, right, so as I told you in the previous slide, we have this combined effect of how much gas you have and how efficiently you turn the gas into stars. And all of that combined shapes the galaxy population. Now, how much gas you have, that comes from sort of where you are in the cosmic web, how much gas you can bring in along these filaments. So that's determined on very, very large scales. Now, how efficiently you convert the gas into stars, that is determined on very small scales, right? Star formation is a process that happens on much, much smaller scales, well within the galaxies. And that is sort of the new challenge, and what's really a new development in our studies of galaxy evolution recently is that to be able to really understand things, we need to connect the largest scales of the universe to the smallest scales where stars are forming. And particularly that last point is something that has been quite an eye-opening discovery. So because there used to be this fundamental belief, or based on observation, that star formation efficiency was sort of constant across all galaxies. You have a certain amount of gas, you form a certain amount of stars. This is what we call, for example, the Koenig-Schmidt relation, as illustrated here. It's a fundamental ingredient that goes into simulations of galaxy evolution. So it's something that we rely on quite a lot. But through our surveys, what we're finding are these systematic variations of the efficiency of galaxies at making stars, across the population. So that leads to some important questions, but we're finally at the point where we can get answers to this thanks to new facilities like ALMA and the NOEMA interferometer. So this is some really, really exciting things that are coming up. But so in summary, what this shows, so if we take some high-resolution images of galaxies and we can identify the individual molecular clouds in them, count them, calculate their masses, and so on. So what these plots show, let's just look at the bottom line. So that shows, so what's the mass of the most massive clouds in each galaxy? And you see that correlates with the total mass of the galaxy. So what is a very local thing, what sets the formation of stars, seems somehow to be related with the very large-scale properties of the galaxy. This is quite fundamental. There's really no reason to, right, and if we look back at this, why these flows would eventually influence the small-scale physics of star formation. So this is extremely exciting and something that we are starting to learn a lot more through these observations. Now, I said I'd talk about dust, so I will do that quickly in a couple of minutes. The problem so all the progress that I've illustrated through these examples comes from observation of molecular gas, which we do by looking at emission line of carbon monoxide. It's our best tool to study molecular gas in distant galaxies. However, that tool becomes very inefficient as soon as galaxies start to be, of relatively low masses. So of all the galaxies out there, the ones we can study in detail, like I've just shown you, is relatively limited. So clearly, the next thing is to find a tool that we can apply to much larger sample to really push that forward. And there's a lot of interest in using dust to do that. So very quickly, the idea is that you take an image of a galaxy in the infrared. Using some models, we can convert these measurements into a mass, so an amount. We measure the total mass of dust in these galaxies. And then if we can assume something between the ratio of dust to gas, then we can extrapolate a gas mass from the dust mass. The clear advantage of this is that getting these measurements, these fluxes in the infrared, is relatively easy and cheap, right? You can get thousands of them in the amount of time it would take you to do one observation in molecular gas. The problem is in the later stages of this process. I'll save you the detail, but how you go from the simple measurement to a dust mass measurement and a gas mass measurement is still highly uncertain, right? At the moment, mostly we rely on the assumption that all dust in all galaxies across all time is exactly like dust in the Milky Way galaxy, which, as a starting point is not an unreasonable thing to do, but clearly something we need to refine. So since coming to the UK about 5 years ago now, I've been taking an interest in ensuring our community's involvement in the James Clerk Maxwell Telescope, the JCMT, in Hawaii, because it is a great facility to help us to probe that component, that 1% of the 1%, that dust emission. This is a great machine to study that. So we've been doing a large-scale survey called Jingle, where we, again, take this big picture approach. We try to canvass the entire galaxy population to try to establish more relations, more fundamental rules for how galaxies relate to each other. So what you do, what we're investing a lot of time, and the wonderful people actually doing that work are here today, so I have to thank them as well. So we are applying some very complex statistical tools and as well some very detailed models for dust physics to try to model our observations, to get us a really good understanding of what are the properties of dust across all these galaxies. And for the first time, we're able to find some relations between the dust composition, the temperature, the grain size, and so on, and how that varies across the entire galaxy population. And that will allow us to significantly increase the accuracy of our dust and gas measurements. So kind of stuff I was showing you early on, we'll be able to push that to more distant galaxies, as well to lower mass galaxies in the local universe. So, in conclusion, so whereas the gas, right, the cold gas and the dust, it's really such a tiny amount of the mass of a galaxy. And for all the reasons I've tried to convey, they are absolutely critical tools that we really can't afford to neglect if we want to gain a complete picture of how galaxies form and evolve. And we're at a very, very interesting stage now where it's been exposed that there's no way to understand galaxy evolution without linking to very large and very small scales, which make this a much more complicated problem than we thought, but also a much more exciting one. So there's very much to look forward to.
Amelie, thank you very much indeed. Open for questions. I have one. So you dismissed mergers fairly on in your talk. Is that because you think they don't have anything to do with this, or do you think it's just too difficult to deal with?
No, I mean, so I put that statement there because the merging of galaxies, two small galaxies clumping, forming bigger galaxies, it's vital for some things, but we have plenty of evidence to show it is not the thing that regulates the growth and the star formation.
Yeah, okay, thanks. Other questions, comments? Yes, please.
Have you considered the role of neon? It's a relatively abundant element, and it's the only element which approximates to the physical properties of molecular hydrogen. Now, if a galaxy gets older, there will be more neon there, and might this not affect the efficiency of the condensation of stars?
Yeah, so I mean, there are a vast number of different molecules and atoms that in principle we can use to study the composition of these galaxies. Unfortunately, because in this case we applied this to distant galaxy, I mean, we can observe nothing but the brightest few tracers. So, yeah.
You have
So
to use carbon monoxide because
that's
you
right.
detect it.
That's right.
What I was saying is there's a vast number of marker molecules, but only one approximates to the low temperature behavior of molecular hydrogen. And it also is very difficult to detect.
That's right.
I was just hypothesizing a mechanism whereby increasing amounts of neon affects the efficiency of the condensation of stars, because stars fundamentally are formed from molecular hydrogen. If that is contaminated with increasing amounts of neon, would that not affect efficiency?
Possibly. I mean, not something I can comment on based on these observations.
Okay, that sounds like a very good answer. Okay, thank you, Amelie, very much indeed. Thank you.